Section 2.6, page 3, the last page of this section. So again, I'm given the specific directions to use implicit differentiation, and this is to find the equation of a tangent line to the curve of the folium x cubed plus y cubed equals 6xy, which is actually drawn for us off to the side. Obviously lots of tangent lines, but specifically to the point 3, 3, where x is 3, y is 3, and we can see that we already can kind of tell what our tangent line is going to look like. So to find an equation of a tangent line, I know that I need y minus y1, which they gave me, and x minus x1 that they gave me, but I needed to find a slope. And so to get the slope, I take the derivative of the function. But this is going to require implicit differentiation. So the derivative of x cubed is just 3x squared. The derivative of y cubed, it's not a product rule. It's just the 3y squared. But remember, we took a derivative of y, so I need to list that y prime using implicit differentiation. Equals, and then I went ahead and just thought of the 6 as being left out front, but some people will think of, 6x is the first function and y is the second function. So the derivative of just x is 1 times the second function untouched, plus, because it's a product rule, the derivative of y, which is 1, but we have a y, so we need to put y prime, times the second function, which is x, or maybe you'd put a 6 there. So ultimately, I will end up with a 6 with the first term and a 6 with the second term. But implicit differentiation says once you've taken the derivatives using the implicit differentiation process, I need to isolate those y's. So I've already got a y on the left, and people like to y prime, on the left, and people like to leave those on the left. So I'm going to subtract the other y prime term to the left. I'm going to subtract the 3x squared term to the right. I'm going to factor my y prime out, which leaves me with a positive 3y squared and a minus 6x. That all gets divided to the right side to be in the denominator. We'll talk about some other ways to approach this in a moment. But basically, we knew that we were given an x1 value. We were given a y1 value, but we needed to find the slope. This formula, y prime, is for all the slopes for any point anywhere on this curve, but we specifically want it when x is 3 and y is 3. So where y is, I'm going to be plugging in a 3. Where x is, I'm going to be plugging in a 3. Notice I tried to color coordinate it. My green 3's are where the x value went, and my blue 3's are where the y value went. Now, theoretically, you could have come and plugged the 3's up above in this first line and not solve for this. But sometimes you have part A, do it at 3, 3, and then, part B, do it at the point, -1, 0.2 or whatever that was. So I tend to just isolate the y prime and being familiar with that. So I'm going to do whatever algebra or arithmetic really I get for my slope. And now I have a slope to plug in, distributing the -1, adding the opposite of the -3 to both sides. I've got my answer. And let's look at that, even though I don't have it drawn on the graph. We were taking the slope, we were finding the tangent line when x is 3. We can see that our y value is 3. So we're saying we're going to have this line like this. Notice you have a y-intercept at about 6. You can see that we had a negative slope of down 1 over 1, down 1 over 1. So even though it's possible I made a math mistake somewhere, I feel pretty good that my y-intercept and at least the sign or steepness of my slope seems reasonable.